For most of human history, nobody knew what Andromeda was. It was a curiosity, a blemish in the night sky, noticed by a few careful observers, catalogued by a few meticulous astronomers, but understood by no one. A Persian astronomer named Abd al-Rahman al-Sufi was compiling a comprehensive catalogue of the night sky, a book called the Book of Fixed Stars, which systematically described every star and nebulous object visible to the naked eye. Al-Sufi was working in Isfahan, in what is now Iran, and he was building on the work of the ancient Greek astronomer Ptolemy, whose star catalogue from the 2nd century had been the standard reference for 800 years. Al-Sufi went through Ptolemy's catalogue star by star, verifying positions, correcting errors, and adding objects that Ptolemy had missed. One of the objects he added was the smudge in the constellation Andromeda. He called it a small cloud. That was his entire description, a small cloud. He noted its position, recorded it, and moved on. He did not speculate about what it was. He did not suggest it might be anything other than what it appeared, a faint nebulous patch, presumably a cloud of luminous gas somewhere in the vicinity of the fixed stars. He could not have known, could not possibly have imagined, that he was documenting a structure containing more stars than there are grains of sand on every beach on Earth. Al-Sufi's observation was remarkable for its accuracy and its restraint. He saw what was there, described it honestly, and did not overinterpret. This is the mark of a good observer, and good observers are rarer than you might think. Most people, confronted with something they don't understand, either ignore it or explain it away with whatever theory is convenient. Al-Sufi did neither. He simply wrote it down. Chinese astronomers may have recorded the same object even earlier, though the references in Chinese astronomical texts are ambiguous and difficult to map onto modern identifications with certainty. What is certain is that the smudge was visible to anyone who looked for it, in any culture, at any time in human history when the skies were dark enough. For thousands of years people must have seen it, hunters, navigators, philosophers, priests, and wondered briefly what it was. None of them could have guessed the answer. The smudge entered European astronomical awareness in the early 17th century. Simon Marius, a German astronomer, independently observed it with a telescope in 1612 and described it as resembling the light of a candle shining through horn. This is a lovely description, the warm, diffuse, slightly yellowish glow of the galaxy's central bulge, seen through the haze of its outer disk. Marius didn't know what he was looking at either, but his description captures something about the quality of the light that modern photographs, with their enhanced contrast and extended exposure times, sometimes lose for the next 3 centuries. Andromeda remained exactly what it appeared to be, a nebula. The word comes from the Latin for cloud or mist, and that's what astronomers assumed it was. A cloud of luminous gas somewhere within the Milky Way, of no particular cosmological significance. It was catalogued by Charles Messier in 1764 as the 31st object in his famous catalogue of nebulae and star clusters, hence its designation M31. Messier was a comet hunter, and he compiled his catalogue specifically as a list of annoying objects that might be mistaken for comets. He wasn't particularly interested in the nebulae themselves. They were obstacles, not targets. Other astronomers were more curious. William Herschel, the great English astronomer who discovered Uranus, observed Andromeda with his large reflecting telescopes in the late 18th century and tried to resolve it into individual stars. He couldn't. His telescopes, though the best in the world at the time, lacked the aperture and resolution to separate the light of the galaxy into discrete points. But he suspected that nebulae like Andromeda might be distant aggregations of stars, island universes, as the philosopher Immanuel Kant had speculated in 1755. Kant's idea was prescient but unprovable with the technology of his era. It would take another century and a half to settle the question. By the early 20th century, the question of what the spiral nebulae were had become one of the central controversies in astronomy. Were they gas clouds within the Milky Way, or were they separate galaxies, island universes, far beyond its boundaries? The stakes were enormous. If the spiral nebulae were local, the Milky Way was essentially the entire universe. If they were distant, the universe was vastly larger than anyone had imagined. The controversy came to a head in 1920 in an event known as the Great Debate. Two American astronomers, Harlow Shapley and Heber Curtis, presented opposing views at a meeting of the National Academy of Sciences in Washington, D.C. Shapley argued that the Milky Way was enormous, far larger than previous estimates, and that the spiral nebulae were relatively nearby objects within it. He pointed to observations suggesting that the Milky Way was at least 300,000 light-years across, large enough to contain the spiral nebulae as internal structures. He also cited a measurement by Adriaan van Maanen, a respected astronomer at Mount Wilson Observatory, who claimed to have detected rotation in the spiral nebula M101. If M101 were truly rotating at the rate van Maanen measured, and if it were at the great distances proposed by the island universe hypothesis, then the outer parts of the spiral would be moving faster than the speed of light, which was physically impossible. This was a powerful argument. If van Maanen's measurement was correct, the spiral nebulae had to be nearby. Curtis argued the opposite. He presented evidence that the spiral nebulae were independent star systems far beyond the Milky Way. He pointed out that novae, exploding stars, had been observed in Andromeda and other spiral nebulae, and that these novae were much fainter than novae in the Milky Way, implying great distance. He also noted the presence of dark lanes in some spiral nebulae, features that resembled the dust lanes seen in the Milky Way, suggesting a structural similarity between the spirals and our own galaxy. Curtis's estimate of the Milky Way's size was smaller than Shapley's, leaving room for the spiral nebulae to exist outside it. The debate was not resolved that evening. Both men made valid points, and the available evidence was genuinely ambiguous. Van Maanen's rotation measurement, which was Shapley's strongest argument, turned out to be wrong, a systematic error in his photographic measurements that he never acknowledged. But this wasn't established until years later. In 1920, the data was insufficient to settle the question. The resolution came in 1924 from a man who was, by temperament, more observer than debater. Edwin Hubble, a former lawyer, former boxer, former Rhodes Scholar, a man of considerable ego and considerable ability, was using the 100-inch Hooker telescope at Mount Wilson Observatory to study the spiral nebulae. The Hooker telescope, completed in 1917, was the largest telescope in the world, and it had the resolution to do something that no previous telescope could manage. It could resolve individual stars within the Andromeda Nebula. Hubble took long exposure photographs of Andromeda, and in those photographs he found what he was looking for. Not just individual stars, he could see those, but a specific type of star, Cepheid variables. The importance of Cepheid variables to this story and to all of cosmology cannot be overstated. So let me explain what they are and why they matter. A Cepheid variable is a star that pulsates. Its brightness increases and decreases in a regular periodic cycle, sometimes over a few days, sometimes over a few weeks or months. The pulsation is driven by a physical mechanism called the Kappa mechanism, involving the ionization and deionization of helium in the star's outer layers. When helium is ionized, it becomes more opaque, trapping heat and causing the star to expand. When the star expands, it cools, the helium deionizes and becomes more transparent, heat escapes, and the star contracts. The cycle repeats, producing a regular oscillation in brightness. The critical discovery about Cepheids was made in 1912 by Henrietta Leavitt. Leavitt worked at the Harvard College Observatory not as an astronomer but as a computer, one of a group of women hired by the observatory director Edward Charles Pickering to catalogue and analyze photographic plates. The women were paid 25 cents an hour. They were not permitted to use the telescopes. They were expected to perform tedious repetitive measurements, classifying stars by brightness and spectral type, and nothing more. Leavitt did more. While studying variable stars in the small Magellanic Cloud, a small satellite galaxy visible from the southern hemisphere, she noticed something remarkable. Among the Cepheid variables she catalogued, there was a clear relationship between the period of pulsation and the brightness of the star. Stars with longer periods were brighter, stars with shorter periods were dimmer. The relationship was tight, consistent, and unmistakable. This was momentous because of a subtlety that might not be immediately obvious. All the Cepheids Leavitt studied were in the small Magellanic Cloud. They were all at approximately the same distance from Earth. This meant that differences in their apparent brightness were real differences in their intrinsic luminosity, not artifacts of distance. A Cepheid that appeared twice as bright as another really was twice as luminous because they were both at the same distance. The period luminosity relationship gave astronomers something they had never had before, a way to determine the intrinsic brightness of a star from a single observable quantity, its period of pulsation, measure a Cepheid's period. Use the period luminosity relationship to determine its true brightness. Compare that to its apparent brightness, how bright it looks from Earth. The difference tells you the distance. This is the principle of the cosmic distance ladder, and Cepheids are its most important rung for measuring distances to nearby galaxies. Hubble found Cepheids in Andromeda. He measured their periods. He calculated their true brightnesses using Leavitt's relationship. He compared those to their apparent brightnesses, and he derived a distance of approximately 900,000 light-years. This was a dramatic underestimate. The true distance is about 2.54 million light-years because Hubble was using an incorrect calibration. He didn't know that there are actually two distinct types of Cepheids, classical Cepheids and W Virginis stars, with different period luminosity relationships. He was applying the wrong relationship to the wrong type of star, which systematically underestimated the distance. This error wasn't discovered until the 1950s when Walter Baade, also working at Mount Wilson, identified the two populations and recalibrated the distance scale. But even Hubble's underestimate was sufficient to prove the point. 900,000 light-years was far, far beyond any plausible boundary of the Milky Way. Andromeda was not inside our galaxy. It was another galaxy, a separate system of stars, comparable in size and complexity to the Milky Way, separated from us by a gulf of empty space that dwarfed every distance previously contemplated by astronomy. The announcement was published in January 1925 in a paper presented at a meeting of the American Astronomical Society. The universe in a single stroke became incomparably larger. The Milky Way was not everything. It was one galaxy among what would eventually prove to be hundreds of billions. Hubble's discovery was not just an astronomical milestone, it was a philosophical revolution. The change in scale from a universe consisting of a single galaxy to a universe containing billions was comparable to the Copernican revolution, which moved the Earth from the center of the universe to an orbit around the Sun. In both cases, humanity's place in the cosmos was dramatically diminished. We were not at the center of a single bounded system. We were on a small planet orbiting an ordinary star in an ordinary galaxy in a universe of breathtaking, almost incomprehensible vastness. And Andromeda was the gateway to that understanding, the first galaxy beyond our own to be recognized as such. The smudge that Al-Sufi called a small cloud turned out to be the key that unlocked the true scale of the cosmos. Let me try to make the distance to Andromeda feel real, because numbers at this scale, 2.54 million light-years, are so large that they become abstractions. The human brain is not equipped to process numbers with 18 zeros. We need comparisons, analogies, stepping stones. Light travels at 299,792 kilometers per second. In round numbers, 300,000 kilometers per second. This is the fastest speed that anything in the universe can travel. Not just the fastest speed we've achieved, but the fastest speed that is physically possible. Nothing with mass can reach it. Only massless particles, photons, travel at exactly this speed. In 1 second, light covers enough distance to circle the Earth 7.5 times. In 8 minutes and 20 seconds, light crosses the distance from the Sun to the Earth, about 150 million kilometers. This distance, the Earth-Sun distance, is the fundamental unit of solar system astronomy, called the astronomical unit. In 1 year, light covers roughly 9.46 trillion kilometers. This is a light year, not a measure of time, despite the name, but a measure of distance. The distance that light travels in 1 year. The nearest star beyond the Sun, Proxima Centauri, is 4.24 light-years away. Its light takes a little over 4 years to reach us. The center of our own galaxy, the Milky Way, is about 26,000 light-years away. Its light has been traveling since the last ice age was beginning. Andromeda is 2.54 million light-years away. Its light has been traveling since before the genus Homo existed. When those photons began their journey, the most advanced primates on Earth were Australopithecines, creatures that walked upright but had brains about a third the size of ours, used simple stone tools, and had no language, no fire, no art. Everything that we consider distinctly human, agriculture, writing, mathematics, music, science, philosophy, cities, nations, happened during the time those photons were in transit. In kilometers, the distance to Andromeda is approximately 24 quintillion, that is 24 followed by 18 zeros. This number is meaningless without comparison, so here are some comparisons. The fastest spacecraft ever built by humans is the Parker Solar Probe, which reaches speeds of about 700,000 kilometers per hour during its closest approaches to the Sun. At this speed, the absolute fastest that human engineering has ever achieved, the journey to Andromeda would take approximately 3.9 billion years. The Earth is about 4.5 billion years old. You would depart from a young, half-formed planet and arrive at Andromeda after a span of time during which back home the entire history of complex life would unfold, from the first cells to the first fish, to the first land animals, to the dinosaurs, to the mammals, to the hominids, to you. Voyager 1, launched in 1977, now the most distant human-made object, traveling at about 61,000 kilometers per hour, would need over 44 billion years to reach Andromeda. The universe itself is only 13.8 billion years old. Voyager would need more than 3 times the current age of the cosmos to make the trip. Even at the speed of light, the universal speed limit, the journey would take 2.54 million years. You could depart Earth at the moment of your birth, travel at the maximum speed that physics permits, and arrive at Andromeda after a span of time during which dozens of ice ages could come and go. Human civilization could rise and fall thousands of times, and the species Homo sapiens might well evolve into something unrecognizable or go extinct entirely. Andromeda is not just far away, it is unreachable, it exists in a place that we can see but can never visit, can study but can never touch. Every piece of information we have about it, every measurement of its mass, its size, its composition, its structure, its history, its future, has been extracted from photons. Light that left the galaxy millions of years ago and crossed the void to our instruments. We have never been to Andromeda. We have never sent a probe. We have only caught the light and read what it carried. This is the astonishing thing about astronomy. It is a science conducted entirely through passive observation. No experiments, no controlled conditions, no laboratory, just light, arriving from very far away, encoded with information about its source. And from that light we have reconstructed the structure and history of a galaxy of 1 trillion stars with sufficient precision to predict its future billions of years in advance. The capacity of the human mind to extract knowledge from photons is, when you think about it, one of the most remarkable capabilities that evolution has ever produced. Now let me take you inside the galaxy itself. Andromeda is a barred spiral galaxy, classified as type SASB in the de Vaucouleurs system. This technical designation tells you several things. S means spiral. It has a disk with spiral arms. A means it's not strongly barred, though recent infrared observations have revealed a modest bar structure at the center that was previously hidden by dust. This means the spiral arms emerge from the ends of the bar or from the central region without a well-defined ring. And B describes the tightness of the spiral arms, neither tightly wound nor loosely wound, but somewhere in between. In less technical terms, Andromeda is a large, magnificent spiral galaxy, similar in basic structure to our own Milky Way, but substantially larger. The disk, the flat, rotating plane, where most of the stars live, spans approximately 220,000 light-years in diameter. Let me put this in perspective. If you could somehow travel at the speed of light from one edge of Andromeda's disk to the other, the journey would take 220,000 years, longer than Homo sapiens has existed as a species. You would depart before the earliest cave paintings, before the first anatomically modern humans left Africa, before any of the cultures, languages, or civilizations that define our species had come into being. And you would arrive 220,000 years later at the other side of a single galaxy. The Milky Way's disk, for comparison, spans about 100,000 light-years. Andromeda is roughly twice as wide, a substantially larger galaxy by this measure. The disk is thin relative to its width, about 1,000 light-years thick in most places, though it varies. This thinness is a consequence of rotation. As the proto-galactic gas cloud collapsed under its own gravity billions of years ago, random motions were damped by collisions between gas particles. The motions that survived were those in the direction of the net angular momentum, the overall spin. The gas settled into a rotating disk perpendicular to the spin axis, like pizza dough flattening as it spun. Stars that formed from this gas inherited its rotation, and the disk has been maintained by the balance between gravitational pull inward and centrifugal force outward ever since. The disk doesn't rotate like a solid wheel. Different parts rotate at different speeds, a phenomenon called differential rotation. Stars near the center complete their orbits in tens of millions of years. Stars in the outer disk take hundreds of millions of years. Stars in the outermost regions take over 1 billion years to complete a single orbit. This differential rotation is essential to the formation and maintenance of the spiral arms, as I'll explain shortly. The total number of stars in Andromeda is estimated at roughly 1 trillion, a number that is used so casually in astronomical and economic contexts that it has lost its visceral impact. Let me try to restore it. If you counted Andromeda's stars at a rate of 1 per second, 24 hours a day, without ever pausing to sleep, eat or rest, you would need approximately 31,700 years to count them all. You would begin counting around the time that humans were painting the walls of the Chauvet cave in France, some of the oldest known art in the world, and you would finish counting far in the future, long after every structure currently standing on Earth had crumbled to dust. Each of those trillion stars is a thermonuclear reactor, a sphere of plasma, fusing lighter elements into heavier ones in its core, radiating energy into space as light and heat. Some are far larger than our Sun, blue supergiants 100 times more massive, burning through their fuel in a few million years and dying in spectacular explosions. Some are far smaller, red dwarfs a tenth the Sun's mass, sipping their hydrogen so conservatively that they will burn for trillions of years, far longer than the current age of the universe. Most of Andromeda's stars, indeed most stars in any galaxy, are red dwarfs. They're the quiet majority, too dim to see individually at Andromeda's distance, but collectively accounting for the bulk of the stellar population. And around many of these stars there are planets. We cannot see them, no telescope exists or is planned that could resolve individual planets at Andromeda's distance, but we know they must be there. In our own galaxy, every star we've studied carefully enough appears to have planets. The Kepler Space Telescope, which stared at a single patch of sky for 4 years and measured the brightnesses of over 150,000 stars, found that planets are at least as common as stars. Many stars have multiple planets. Some have rocky worlds in their habitable zones, the range of distances where liquid water could exist on the surface. There is no reason to think that Andromeda, which is made of the same elements and governed by the same physics, would be any different. 1 trillion stars, potentially several trillion planets, billions of them potentially habitable. At the center of Andromeda sits a supermassive black hole. Every large galaxy appears to harbor one, a black hole with a mass of millions or billions of times the mass of the Sun, sitting at the gravitational center of the galaxy. Andromeda's central black hole has a mass of approximately 140 million solar masses. To put this in perspective, the black hole at the center of our own Milky Way, Sagittarius A, has a mass of about 4 million solar masses. Andromeda's black hole is approximately 35 times more massive. A black hole of this mass has an event horizon, the boundary beyond which nothing, not even light, can escape, with a radius of roughly 400 million kilometers. That's about 2.7 astronomical units, slightly less than the distance from the Sun to the asteroid belt. If you place this black hole at the center of our solar system, it would extend beyond the orbit of Mars. Its gravitational influence would reshape the inner solar system entirely. But the black hole's gravitational dominance extends far beyond its event horizon. The region within which the black hole's gravity significantly affects stellar orbits, called the sphere of influence, extends thousands of light years from the center. Stars within this region orbit the black hole at high speeds, their trajectories determined primarily by the black hole's mass rather than by the combined mass of surrounding stars. Measuring these stellar orbits, their speeds, their shapes, their orientations, is one of the primary methods by which astronomers determine the black hole's mass. The faster the stars orbit, the more massive the black hole must be to hold them in those orbits. The black hole is currently quiescent. It is not actively consuming large amounts of matter. There is no brilliant accretion disk, no relativistic jet, no intense X-ray emission from infalling material. The black hole is, in a metaphorical sense, sleeping, but this sleep is not permanent. If a sufficiently large cloud of gas, or an unfortunate star, were to wander within the black hole's tidal radius, the distance at which the black hole's gravitational gradient is strong enough to tear an extended object apart, the material would be stretched, heated, and consumed. Gas would spiral inward, forming an accretion disk that would heat to millions of degrees and radiate intensely across the electromagnetic spectrum. Jets of plasma might erupt from the poles of the spinning black hole, accelerated to nearly the speed of light by magnetic fields twisted in the accretion flow. Andromeda would flare into activity, transforming from a quiet spiral galaxy into an active galactic nucleus, a beacon visible across cosmological distances. This has almost certainly happened before, perhaps many times, during Andromeda's 12-billion-year history. Most large galaxies are thought to have gone through active phases, particularly during the early universe, when gas was plentiful, galaxy mergers were frequent, and the central black holes were growing rapidly. Each active phase would have lasted millions of years, during which the black hole consumed vast quantities of gas and grew more massive. The 14 million solar masses that Andromeda's black hole contains today are the accumulated legacy of billions of years of intermittent feeding. For years, there was a fascinating puzzle about Andromeda's nucleus. Hubble Space Telescope images showed what appeared to be a double nucleus, two bright concentrations of light at the very center of the galaxy, separated by a few light years. This raised the tantalizing possibility that Andromeda contained two supermassive black holes, perhaps the remnants of a past galaxy merger, two black holes that had spiraled inward but not yet completed their merger. Binary supermassive black holes are predicted by theory. Whenever two galaxies merge, their central black holes should eventually sink to the center of the merged system and form a binary, but observational confirmation has been extremely difficult. The current consensus, established through detailed spectroscopic observations and dynamical modeling, particularly from around 2005 onward, and refined through the 2010s and early 2020s, is that the double nucleus is not two black holes, but one black hole surrounded by an eccentric disk of stars. The stars orbit the black hole on elongated elliptical paths, and they bunch up at the far end of their orbits, the point where they move most slowly, just as a planet moves most slowly at the far point of an elliptical orbit. This bunching creates a concentration of starlight offset from the black hole, producing the appearance of a second nucleus. The geometry is beautiful and counterintuitive. The brighter of the two apparent nuclei is actually the one farther from the black hole, because that's where the stars spend most of their orbital time. The central bulge, the bright, roughly spherical concentration of stars surrounding the black hole, spans about 30,000 light-years across. To appreciate this, consider that 30,000 light-years is almost a third of the entire diameter of the Milky Way. Andromeda's bulge alone is nearly as large as a moderately sized galaxy. The bulge contains several 100 billion old stars, population 2 stars, as astronomers designate them. These stars formed early in the galaxy's history, when the universe was only 1 billion or 2 years old, from gas that contained very few elements heavier than hydrogen and helium. They are metal poor in the peculiar language of astronomy, where metal means any element heavier than helium, carbon, oxygen, nitrogen, silicon, iron, everything that makes up rocky planets and living organisms. These elements didn't exist in the early universe. They were created later in the cores of stars and in the explosions of supernovae, and gradually accumulated in the interstellar gas over billions of years of stellar evolution. The old stars of the bulge glow predominantly in red and yellow wavelengths. They are cool, evolved stars, many of them red giants, stars that have exhausted the hydrogen fuel in their cores and expanded enormously. A red giant can be 100 times the diameter of the Sun. Some of Andromeda's red giants are larger than the orbit of Earth. They are the end stage of stellar life for medium-mass stars. the phase that our own Sun will enter in about 5 billion years, swelling to engulf Mercury and Venus before shedding its outer layers and leaving behind a white dwarf core. If you could somehow visit a planet near the center of Andromeda's bulge, setting aside the intense radiation environment that would make such a place uninhabitable, the night sky would be utterly unlike anything visible from Earth. The stellar density near the center of a galactic bulge is thousands of times higher than in our solar neighborhood. Thousands of stars would be bright enough to cast shadows. The combined starlight would create a perpetual twilight, a sky filled with suns in every direction, drowning out the darkness. The concept of night would not exist. There would be no dark sky to reveal the faint smudge of a neighboring galaxy. From the center of Andromeda, you would be surrounded by so much light that the universe beyond the galaxy would be invisible. Moving outward from the bulge, we enter the disk, and here the galaxy comes alive with activity. The spiral arms, the defining visual feature of Andromeda, are not solid structures. This is one of the most important and counterintuitive facts about spiral galaxies, and it took astronomers decades to figure out. If the spiral arms were material structures, if they were made of specific stars that stayed together as the arms rotated, then the galaxy's differential rotation would wind them up. Stars near the center orbit faster than stars in the outskirts. Over time, this would stretch the arms, wrapping them tighter and tighter around the center, like winding a spring. After a few rotations, a billion years or so, the arms would be wound so tightly that they'd be indistinguishable from the rest of the disk. But Andromeda has been rotating for 12 billion years, and its spiral arms are still clearly defined. Something keeps them from winding up. The solution, proposed independently by C.C. Lin and Frank Shu in 1964 and by L.R. Toumre around the same period, is that spiral arms are density waves, not material structures but patterns. The arms are regions of higher than average density moving through the disk at a speed different from the speed of the stars. Individual stars enter a spiral arm, spend time in the compressed region, and then move on. The arm persists, but the stars composing it are constantly changing. The best analogy is a traffic jam on a highway. Cars approach the jam, slow down, bunch together, and then accelerate out the other side. The jam itself moves, often backward relative to the traffic flow, but the individual cars pass through it. The jam is not made of specific cars. It's a pattern that persists even as different cars participate in it at different times. In a spiral galaxy, the density wave compresses gas as well as stars, and this compression is what makes the spiral arms visible. When interstellar gas is compressed, it can reach the critical density needed for gravitational collapse, the threshold at which a cloud's self-gravity overcomes its internal pressure and the cloud begins to contract. This triggers star formation. New stars are born in the compressed region in the spiral arm, and the most massive, most luminous of these new stars are what make the arm bright. O and B type stars, the hottest, most massive stars, are extraordinarily luminous. A single O-type star can outshine the Sun by a factor of several 100,000. These stars burn a brilliant blue-white and flood their surroundings with ultraviolet radiation that ionizes the hydrogen gas around them, causing it to glow in the distinctive pinkish-red light of H-alpha emission, the signature of ionized hydrogen. These glowing regions are called HII regions, and they dot the spiral arms like jewels on a necklace, but O and B stars pay for their brilliance with brevity. They burn through their nuclear fuel so quickly that they live only a few million years, an eye blink in cosmic terms. A star born in a spiral arm will die in that same arm or very close to it, because it simply doesn't have time to migrate away before its fuel runs out. This is why the arms are bright and blue, They contain concentrations of young, massive, short-lived stars that were born there and will die there. The rest of the disk between the arms contains older, dimmer, longer-lived stars that have drifted away from their birthplaces over billions of years. Andromeda's spiral structure is not perfectly symmetrical. One arm is more prominent than the other. The disk is slightly warped. There are asymmetries and disturbances that point to a violent past. Evidence from stellar streams, chemical abundances, and dynamical models strongly suggests that Andromeda experienced a major merger with another large galaxy approximately 2 billion years ago. Some estimates place this event closer to 800 million years ago, and the debate continues. The collision disrupted the orderly spiral pattern, warped the gas disk, and left behind debris in the form of stellar streams and tidal features that are still visible today. Computer simulations of galaxy mergers show that it takes billions of years for the disturbed structure to relax back into symmetry. Andromeda is still in the process of recovery. The galaxy we see today is not in a steady state. It's a snapshot of a system that was recently perturbed and is gradually settling back into equilibrium. Recently, in this context, means within the last billion years or so. Galactic timescales are long. There's a particularly striking feature in Andromeda's disk that deserves special attention. About 32,000 light-years from the center, there is a prominent ring of enhanced star formation. This ring blazes in ultraviolet images, a nearly complete circle of young hot stars, stellar nurseries, and glowing nebulae. It's one of the most active star-forming regions in the galaxy, producing new stars at a rate substantially higher than the surrounding disk. The ring's origin is debated. It may be related to a resonance with the central bar, a specific orbital radius where the gravitational dynamics of the bar create conditions favorable for gas accumulation and star formation. Bars in spiral galaxies are known to redistribute gas, driving it inward or outward along the bar and piling it up at specific resonance radii. The 32,000 light-year ring may be one such pile-up, a place where the bar's gravity has concentrated gas, triggering a burst of star formation. Alternatively, the ring may be related to the past merger event. When a smaller galaxy plunges through a larger one, it can create ring-like density waves that expand outward through the disk, like the ripple from a stone dropped in a pond. These ring waves compress gas and trigger star formation in a propagating front. Some models of Andromeda's merger history produce ring structures at approximately the observed radius. The two explanations are not mutually exclusive. The ring may result from a combination of bar dynamics and merger-induced perturbations, both working together to concentrate gas at a specific radius. Disentangling these effects requires detailed numerical simulations that model both the bar and the merger simultaneously, work that is ongoing. Within the spiral arms lie the molecular clouds, the coldest, densest, darkest regions of the interstellar medium. These clouds are the wombs in which stars are born, and they are remarkable objects in their own right. A typical giant molecular cloud spans 100 to 300 light-years and contains enough gas and dust to build millions of stars. The gas is primarily molecular hydrogen, two hydrogen atoms bonded together, along with carbon monoxide, ammonia, water vapor, methanol, formaldehyde, and a surprising variety of more complex organic molecules. The chemistry of molecular clouds is far richer than anyone expected when they were first studied in the 1970s. Molecules containing 10, 20, even 60 or 70 atoms have been detected in interstellar clouds in our own galaxy. Amino acids, the building blocks of proteins, have been found in meteorites that formed from material in the solar nebula, which itself was a molecular cloud. The chemical precursors of life are produced naturally in vast quantities in the same clouds that give birth to stars. The interior of a molecular cloud is extraordinarily cold, typically about 10 to 20 Kelvin, roughly minus 250 to minus 260 degrees Celsius. At these temperatures, gas molecules move sluggishly, thermal pressure is low, and gravity has the upper hand. The cloud is on the verge of collapse. What prevents it from collapsing immediately is a combination of internal turbulence, chaotic, supersonic motions of the gas, magnetic fields that thread through the cloud and provide additional support, and angular momentum that resists contraction. When a perturbation, the passage of a density wave, the shock from a nearby supernova, the collision of two clouds pushes a region of the cloud past the critical density, the balance tips, gravity wins, the region begins to collapse. As it contracts, it heats up, and conservation of angular momentum causes it to spin faster and flatten into a disk, the protostellar disk, the birthplace of planets. At the center of the disk, the gas becomes dense and hot enough to initiate nuclear fusion. Hydrogen nuclei, protons begin to fuse into helium nuclei, releasing energy. A star is born. The process takes about 100,000 years from initial collapse to fusion ignition, fast by cosmic standards, though still 100 times longer than recorded human history. The newly born star illuminates its surroundings, heating the remaining gas and dust, blowing out a cavity in the molecular cloud with its stellar wind and radiation. If the star is massive enough, more than about 8 solar masses, its ultraviolet radiation ionizes a large volume of surrounding hydrogen, creating an HII region that glows brightly in pinkish-red light. If it's less massive, the effects are subtler, a small warm cocoon of heated gas and dust, visible primarily in infrared wavelengths. Most of the gas in a molecular cloud does not end up in stars. Star formation is remarkably inefficient. Only about 1 to 10% of a cloud's mass is converted into stars before the cloud is disrupted by the energy output of its own stellar progeny. The rest is blown away, heated, dispersed, and recycled back into the interstellar medium, where it may eventually participate in the formation of another generation of stars. This recycling is essential. It's what makes galaxies dynamic, evolving systems rather than static collections of stars. Gas forms stars. Stars evolve, produce heavy elements through nuclear fusion, and return those enriched materials to the interstellar medium when they die, through stellar winds, planetary nebulae, and supernovae. The enriched gas mixes with pristine gas, forms new stars and planets, and the cycle repeats. Each generation of stars is slightly richer in heavy elements than the previous one. The Sun, born about 4.6 billion years ago, contains about 2% heavy elements by mass, the accumulated legacy of multiple generations of stellar enrichment over the previous 8 or 9 billion years of the galaxy's history. This chemical evolution has profound consequences. Without heavy elements, rocky planets cannot form. Without rocky planets, there is no solid surface on which liquid water can pool, no substrate for complex chemistry, no platform for life. The very existence of Earth and of every living thing on it depends on the deaths of stars that lived and died before the Sun was born. We are, in the most literal sense, made of stellar debris. The same processes operate in Andromeda. The same chemical enrichment has occurred. The same heavy elements, carbon, nitrogen, oxygen, silicon, iron, have been produced by the same nuclear reactions in the same types of stars. Andromeda's younger stars, like the Sun, contain the full complement of heavy elements needed for planet formation and potentially for life. The galaxy is a chemical factory, producing the ingredients of complexity on a trillion-star scale. Andromeda currently forms new stars at a rate of about 1 solar mass per year. This is modest, far below the galaxy's peak star formation rate, which probably occurred several billion years ago. perhaps during or shortly after the major merger event. The Milky Way forms stars at roughly the same rate, despite being smaller. This means that both galaxies are in a relatively quiet, mature phase of their evolution, still active, still producing new stars, but at a pace that is gradually declining as the raw material molecular gas is used up. The total mass of molecular gas in Andromeda is about 8 billion solar masses. Add the atomic hydrogen, neutral gas that hasn't yet condensed into molecular form, and the total gas reservoir is perhaps 20 billion solar masses. This sounds like a lot, but compared to the total stellar mass, several hundred billion solar masses, it's a small fraction. Most of the gas has already been converted into stars. The galaxy is running out of fuel. Star formation will continue for billions of years to come, but at ever-decreasing rates as the gas supply dwindles. Let me now talk about something that dominates Andromeda's mass budget, but remains one of the deepest mysteries in physics: dark matter. When astronomers measure the rotation speed of gas and stars at different distances from Andromeda's center, using the Doppler shift of spectral lines to determine how fast material is moving toward or away from us, they find something that defies naive expectation. In the solar system, planets farther from the Sun orbit more slowly. Neptune moves much more slowly than Mercury because the Sun's gravitational pull weakens with distance. You would expect the same behavior in a galaxy. Stars and gas farther from the center should orbit more slowly because the gravitational pull of the visible matter is weaker at larger distances, but they don't. The rotation speed remains roughly constant, flat out to enormous distances from the center. Stars in the outer disk orbit just as fast as stars much closer in. This flat rotation curve, first measured for several galaxies by Vera Rubin and Kent Ford in the 1970s, is the signature of dark matter. The visible matter, stars, gas, dust, cannot account for the gravitational pull needed to maintain these high orbital speeds at large distances. There must be additional mass, invisible mass, providing extra gravitational pull. This invisible mass, dark matter, is distributed in a vast, roughly spherical halo that extends far beyond the visible disk. The dark matter halo of Andromeda is thought to reach at least 600,000 light-years from the center, and possibly farther, several times the radius of the visible disk. The total mass of the dark matter halo is estimated at 1.2 to 1.5 trillion solar masses, making it the dominant mass component of the galaxy. For every kilogram of normal matter atoms, the stuff we can see and touch, there are roughly 5 to 6 kilograms of dark matter. The beautiful spiral disk of stars and gas that we photograph and admire is merely the luminous tip of a much larger invisible structure. We do not know what dark matter is. This statement is worth making plainly because it is one of the most important open questions in all of science. Dark matter doesn't emit light at any wavelength, it doesn't absorb light, it doesn't scatter light, it doesn't interact with normal matter through the electromagnetic force at all. The only way we know it's there is through its gravitational effects, the flat rotation curves, the gravitational lensing of background galaxies, the dynamics of galaxy clusters, the patterns in the cosmic microwave background radiation. Physicists have proposed many candidates. Weakly interacting massive particles, WIMPs, were the leading hypothesis for decades. These would be heavy particles produced in the early universe, interacting with normal matter only through gravity and the weak nuclear force. Experiments in deep underground laboratories have been searching for WIMPs since the 1990s, using ultra-sensitive detectors shielded from cosmic rays by kilometers of rock. So far, nothing has been detected. The allowed parameter space for WIMPs is shrinking. Actions are another candidate, very light particles, originally proposed to solve a problem in quantum chromodynamics that could make up dark matter if they exist in sufficient abundance. Experiments using strong magnetic fields and microwave cavities are searching for axions, no detection yet. Sterile neutrinos, primordial black holes, gravitinos, and various other exotic particles have been proposed. None have been confirmed. The dark matter particle, if it is a particle, remains undetected after decades of searching. We know dark matter exists, we know how much of it there is, we know roughly how it's distributed. We do not know what it's made of. This is humbling. The substance that makes up about 85% of all matter in the universe, the scaffolding on which galaxies were built, the invisible framework that holds the cosmic web together, is completely unknown to us. We live in a universe whose dominant material component is a mystery, and yet despite this mystery, dark matter's role in galaxy formation is well understood. In the early universe, dark matter clumped together first, forming gravitational potential wells, halos, into which normal matter later fell. The normal matter gas could cool by radiating energy, losing thermal pressure and collapsing further, eventually fragmenting into stars. The dark matter could not cool. It doesn't interact electromagnetically, so it can't emit photons and radiate away its kinetic energy. It settled into a diffuse, extended halo, providing the gravitational framework within which the luminous galaxy assembled. Without dark matter, galaxies like Andromeda could not exist. The gravity of normal matter alone would not have been sufficient to pull together structures of this size in the time available since the Big Bang. Dark matter is not an incidental detail. It is the foundation on which all visible structure in the universe is built. Beyond the visible disk, beyond the spiral arms and the molecular clouds and the star-forming regions, lies the halo, a vast, roughly spherical distribution of old stars, globular clusters, and the scattered debris of consumed satellite galaxies. The stellar halo extends to at least 500,000 light-years from Andromeda's center, more than twice the radius of the visible disk. It contains only about 1% of the galaxy's stars, but spread over such an enormous volume that the stellar density is incredibly low. If you were on a planet in the outer halo, the nearest star might be several hundred light-years away, 50 to 100 times farther than the nearest star to our Sun. The sky would be spectacularly dark, with only a few scattered points of light visible to the naked eye. The core of Andromeda would dominate one portion of the sky as a brilliant, concentrated glow, but the rest of the sky would be emptier than any sky visible from Earth. The halo stars are almost exclusively old, metal-poor stars. Population 2, they formed early in the galaxy's history, before the disk had assembled from gas that had not yet been enriched by many generations of stellar evolution. Some halo stars may be among the oldest objects in the universe, 12 billion years old or more, born when the cosmos was less than 2 billion years old. Mixed in with these ancient stars are the remnants of something more violent, the stellar streams, tidal tails, and debris fields left behind by the destruction of satellite galaxies. When a smaller galaxy falls into Andromeda, captured by the larger galaxy's gravity, it doesn't survive long. Tidal forces, the difference in gravitational pull between the near side and far side of the satellite, stretch the smaller galaxy, pull out streams of stars from its leading and trailing edges, and gradually tear it apart. The stars from the satellite are strewn along its former orbit, forming a thin, elongated stream that wraps around the galaxy like a ribbon. These streams are fossils. Each one records a past act of galactic cannibalism, a smaller galaxy consumed and digested by Andromeda. By mapping the positions and motions of stream stars, astronomers can reconstruct the orbit and mass of the original satellite, even though the satellite itself no longer exists as a coherent entity. This is galactic archaeology, using the scattered remnants of past events to read the history of the galaxy. The Pan-Andromeda Archaeological Survey, PANDAS, used the Canada-France-Hawaii telescope to image an enormous area around Andromeda, covering most of the halo. The survey revealed a rich tapestry of substructure, dozens of stellar streams, shells, and overdensities, each one the ghost of a consumed galaxy. The picture that emerged was striking. Andromeda has been eating its neighbors for billions of years, and the evidence is written across its halo in streams of scattered stars. One particularly prominent feature is the giant stellar stream, a massive river of stars extending from the southern part of Andromeda's disk into the halo. This stream is thought to be the debris of a moderately large galaxy that fell into Andromeda within the last billion years. The stream contains millions of stars, stretched out over hundreds of thousands of light years, still roughly following the orbit of their now destroyed parent galaxy. It is one of the most dramatic examples of galactic tidal disruption visible anywhere in the local universe. Globular clusters, dense spherical concentrations of hundreds of thousands to millions of old stars, are scattered throughout the halo. Andromeda hosts approximately 450 globular clusters, significantly more than the Milky Way's roughly 150. These clusters are among the oldest objects in the galaxy, with ages exceeding 12 billion years. They formed very early, perhaps during the initial collapse of the proto-galactic gas cloud, or in the cores of dwarf galaxies that were later consumed by Andromeda. The most massive globular cluster in Andromeda, Mayol 2, also known as G1, is extraordinary. It contains several million stars packed into a sphere about 100 light-years across. It is roughly twice as luminous as Omega Centauri, the brightest globular cluster in the Milky Way. It is so massive that it almost certainly harbors an intermediate mass black hole at its center, a black hole of perhaps 10 to 20,000 solar masses, smaller than the supermassive black hole at the galaxy's center, but far larger than the stellar mass black holes produced by individual dying stars. There is a growing suspicion that Mayol 2 is not a true globular cluster at all, but rather the stripped nucleus of a former dwarf galaxy. When a small galaxy is torn apart by tidal forces, the outermost stars are stripped away first, leaving behind the dense central core. If the original galaxy had a dense nuclear star cluster, as many dwarf galaxies do, the surviving core would look very much like a globular cluster, old compact metal core containing an oversized black hole. The distinction between massive globular cluster and stripped galactic nucleus may be more semantic than physical. Andromeda is not alone. It is surrounded by a family of satellite galaxies, smaller galaxies held in orbit by Andromeda's immense gravity. At least 35 satellite galaxies are currently known, ranging from substantial dwarf ellipticals to ghostly ultra-faint dwarfs containing only a few thousand stars. These satellites are the survivors of galaxy formation. Small structures that formed in the early universe were captured by Andromeda's gravitational pull and have been orbiting ever since. Some are being torn apart right now. Others are in stable orbits, at least for the moment. The two largest and most prominent satellites are Messier 32 and Messier 110. M32 is a compact elliptical galaxy, small, dense, and remarkably close to Andromeda. It sits only about 24,000 light-years from the larger galaxy's center, practically embedded in its disk. M32 is small, about 8,000 light-years across, but it contains several billion stars and harbors a supermassive black hole of 2 to 4 million solar masses. This black hole is disproportionately massive for such a small galaxy, suggesting that M32 was once much larger. It may have been a substantial galaxy in its own right, perhaps a spiral, that lost most of its outer stars during a close encounter with Andromeda. What we see now is the dense surviving core, the pit of a cherry from which the fruit has been eaten. The tidal forces from Andromeda are continuing to strip away M32's remaining stars. In a few billion years, M32 will be completely destroyed, its stars scattered and absorbed into Andromeda's halo. The supermassive black hole will survive, drifting through Andromeda as a dark, massive object, perhaps eventually spiraling inward to merge with Andromeda's own central black hole. Messier 110 is larger but farther away, about 170,000 light-years from Andromeda's center. It is a dwarf elliptical galaxy, elongated in shape, containing several billion stars. Stellar streams connect it to Andromeda, visible in deep photographs as faint trails of stars being pulled away by tidal forces. M110 is being consumed slowly and inexorably. Its stars are being added to Andromeda's halo, one stream at a time. The smaller satellites, the dwarfs and ultra-faint dwarfs, are among the most intriguing objects in the local universe. Many of them are dominated by dark matter. In some, dark matter outweighs visible matter by factors of hundreds or thousands. These galaxies are almost entirely dark, vast halos of invisible mass with a thin dusting of visible stars, like the faintest possible galaxies, barely distinguishable from the background. These dark matter-dominated dwarfs are valuable for fundamental physics because they provide clean laboratories for studying dark matter's properties in a system where dark matter is the dominant mass component. Its effects on stellar motions are most easily measured by studying the velocities and positions of stars in ultra-faint dwarfs. Astronomers can constrain the density profile of the dark matter halo, how the density changes with distance from the center. Different dark matter candidates predict slightly different density profiles, so precise measurements of dwarf galaxy dynamics can, in principle, help distinguish between competing models. Let me now talk about what will happen when Andromeda and the Milky Way merge, because this is not speculation. It is a prediction grounded in well-understood physics, supported by extensive computer simulations, and as certain as any prediction in astronomy can be. The two galaxies are approaching each other at approximately 110 kilometers per second. This is the radial velocity, the component of the motion along our line of sight. For decades, the transverse velocity, the component perpendicular to our line of sight, was unknown because it's much harder to measure. Transverse motion at Andromeda's distance produces an angular displacement so tiny that it requires measurements of extraordinary precision. Those measurements were finally made in 2012 by a team using the Hubble Space Telescope. By tracking the positions of stars in Andromeda over a baseline of several years and comparing them to background galaxies, the team measured Andromeda's transverse velocity, approximately 17 kilometers per second. This is small, much smaller than the radial velocity, which means the two galaxies are moving almost directly toward each other. The collision is not a glancing blow, it's nearly head-on. In approximately 4 to 5 billion years, the two galaxies will experience their first close encounter. The term collision is conventional but misleading because when galaxies merge, individual stars almost never collide. Stars are incredibly tiny compared to the spaces between them. The Sun is about 1.4 million kilometers in diameter. The nearest star, Proxima Centauri, is about 40 trillion kilometers away. That's a ratio of about 30 million to 1. If you scaled the Sun down to a grain of sand, the nearest star would be another grain of sand about 10 kilometers away. The galaxy is almost entirely empty space. When two galaxies merge, their stellar populations interpenetrate like two clouds of mist passing through each other. The probability of any two individual stars colliding is negligible. What does collide is the interstellar gas. Gas is extended and fills much of the disk's volume. Gas clouds from the two galaxies will crash into each other at relative speeds of hundreds of kilometers per second. The collisions will compress the gas, heat it to extreme temperatures, and trigger enormous bursts of star formation. Millions of new stars will be born in a relatively short period, a starburst that will flood the merging system with the blue-white light of young, massive stars. For a few 100 million years, the merger will be extraordinarily luminous. Gravitationally, the encounter will be violent. The tidal forces generated by the close passage will stretch and distort both galaxies. Long tidal tails of stars will be pulled out, extending for hundreds of thousands of light years into intergalactic space, rivers of stars flowing away from the merging system. The orderly spiral structures will be destroyed. Stars on previously stable circular orbits will be flung onto chaotic eccentric paths. Some stars will gain enough kinetic energy from the gravitational interactions to escape the merged system entirely, becoming intergalactic vagabonds, stars with no galaxy, drifting through the void for eternity. The first passage will not result in an immediate merger. The two galaxies have too much kinetic energy, they'll pass through each other and separate again, but gravity will slow them, stop them, and pull them back together. The second collision will occur, and the third. Each passage will further scramble the stellar orbits, consume more gas in starbursts, and dissipate kinetic energy through dynamical friction, the process by which a massive object moving through a field of lighter objects transfers energy to them and slows down. The simulations run on supercomputers, modeling the gravitational interactions of millions of particles representing stars, gas, and dark matter, show that the merger process takes approximately 3 to 6 billion years from first encounter to final coalescence. During this time, the two galaxies will repeatedly pass through each other, looking different each time, distorted, stretched, compressed, illuminated by bursts of star formation, dark with dust lanes, spectacular and chaotic. The two supermassive black holes will sink toward the center of the merging system through dynamical friction. Each black hole, as it moves through the sea of stars, creates a gravitational wake, a region of higher stellar density behind it that pulls back on the black hole, extracting kinetic energy and causing it to spiral inward. This process is slow. It takes hundreds of millions to billions of years, but it is inexorable. The black holes will eventually find each other at the center of the merged system and form a binary pair, orbiting each other at close range. The binary black hole orbit will decay through two mechanisms. At first, when the separation is still relatively large, parsecs to tens of parsecs, the binary loses energy by ejecting stars that wander into the region between the two black holes. Three-body interactions between the binary and individual stars can extract energy from the orbit, shrinking it. But this process is limited by the supply of stars. Once the binary has ejected all the stars in its vicinity, the orbit stalls. This is called the final parsec problem, and it was a significant theoretical puzzle for years. The solution appears to be that the chaotic stellar orbits produced by the merger continuously supply new stars to the binary's vicinity, preventing the stall. Once the separation shrinks to about 1,000th of a parsec, a few hundred astronomical units, gravitational wave emission takes over. The binary radiates energy and angular momentum as gravitational waves, ripples in the fabric of space-time, predicted by Einstein's general relativity, and the orbit decays rapidly. In the final minutes or hours, the two black holes spiral together in a dramatic crescendo of gravitational wave emission and merge into a single black hole. The merged black hole will have a mass of roughly 144 million solar masses. the sum of the two progenitors minus a few percent that was radiated away as gravitational wave energy, that few percent, perhaps 3 to 5 million solar masses, was converted entirely into gravitational waves during the merger. The energy released in those waves in those last few minutes exceeds the total electromagnetic luminosity of the entire observable universe at that moment. It is the most energetic event that the laws of physics allow, short of the Big Bang itself. The gravitational wave signal from this merger will propagate across the cosmos at the speed of light. If human descendants, or whatever we have become, have gravitational wave detectors operating at that time, they will record the signal with extraordinary clarity. The waveform will encode the masses and spins of the two black holes, the eccentricity of their orbit, and details of the merger dynamics. It will be a direct recording of space-time itself, oscillating in response to the most violent event our local universe has produced in billions of years. The end result, several billion years after the first encounter, will be a giant elliptical galaxy. The orderly disk structures of both spirals will have been destroyed. The stars will be distributed in a roughly spheroidal configuration, a smooth, featureless ball of stars dominated by old red populations with little ongoing star formation. The remaining gas will have been heated by the starburst and the gravitational interactions, making it too diffuse and energetic to collapse and form new stars. The galaxy will be red and dead, as astronomers sometimes describe evolved elliptical galaxies. This merged galaxy has been given various playful names by astronomers: Milkdromeda, Milkomeda, the Milky Way Andromeda hybrid, whatever it's called. It will be one of the largest galaxies in what remains of the local group. It will contain roughly 1.5 to 2 trillion stars, nearly all the stars from both parent galaxies, minus the few percent that were ejected into intergalactic space. The central supermassive black hole will be one of the more massive in the local universe. And the halo will contain the combined debris of every satellite galaxy that either the Milky Way or Andromeda has ever consumed. What about Earth? What about us? By the time the collision occurs 4 to 5 billion years from now, the Sun will be nearing the end of its main sequence lifetime. It will have brightened by perhaps 30 to 40%, enough to make Earth uninhabitable by any definition. The oceans will have evaporated. The atmosphere will have been lost to space. The surface will be a scorched, barren wasteland. A billion years later, the Sun will enter its red giant phase, swelling to perhaps the orbit of Earth or Mars, engulfing the inner planets in its distended outer layers. If Earth itself survives, if its orbit expands enough due to the Sun's mass loss during the red giant phase, to avoid being consumed, it will be a dead, baked cinder orbiting a dying star, in a galaxy that no longer exists in its current form. The night sky above this dead Earth will be spectacular, filled with the distorted, intermingling light of two merging galaxies, brilliant with starbursts, crisscrossed by tidal streamers, but there will be no one to see it, or perhaps there will be. 4 to 5 billion years is a long time. If human civilization survives, or if our descendants, biological or artificial, survive, they might have the technology to relocate to younger star systems in other parts of the galaxy or in other galaxies entirely. They might watch the merger from a safe distance, recording the collision with instruments we can't imagine, understanding it with physics we haven't discovered yet. This is speculative, of course, but the collision itself is not. It is as certain as the sunrise. The physics is understood. The measurements are precise. The simulations are converging. Andromeda is falling toward us, and nothing can stop it. Let me turn to a question that is, I think, the most profound question you can ask about Andromeda, or about any galaxy, the question of life. 1 trillion stars, potentially several trillion planets. A galaxy that has been producing heavy elements, carbon, nitrogen, oxygen, phosphorus, sulfur, the essential ingredients of biochemistry, for 12 billion years, molecular clouds filled with complex organic molecules, water, methanol, amino acid precursors, all detected in interstellar space, not just in our galaxy, but in the kind of chemical environment that Andromeda's molecular clouds almost certainly contain. If life arises readily when conditions allow, and the early emergence of life on Earth within about 700 million years of the planet's formation suggests that it might, then Andromeda should contain an enormous number of living worlds, not just a few, potentially billions, each one with its own biochemistry, its own evolutionary history, its own cascade of contingency and adaptation, oceans teeming with microbes, atmospheres rich with biosignature gases. Perhaps on some fraction of those worlds, complex multicellular life, perhaps on some smaller fraction, intelligence, language, technology, civilizations. We cannot confirm any of this. We cannot even test it. The distance to Andromeda places its planets forever beyond the reach of our observational capabilities. We cannot resolve individual planets in Andromeda. We cannot analyze their atmospheres. We cannot detect their radio emissions. The techniques that work for studying exoplanet atmospheres in our own galaxy, transit spectroscopy, direct imaging with coronagraphs, are completely useless at Andromeda's distance. The angular separation between a planet and its host star, as seen from Earth, is far too small for any conceivable telescope to resolve. This is frustrating. It means that one of the most interesting questions we can ask about Andromeda, does it contain life, is a question we probably cannot answer, at least not with any technology currently imaginable. But let me dwell on the question for a moment, because even the unanswerable questions can teach us something. On Earth, life appeared quickly. The oldest definitive evidence of life dates to about 3.5 billion years ago, fossilized microbial mats called stromatolites. Chemical evidence, isotopic signatures consistent with biological processes, pushes the date back to perhaps 3.8 or even 4.0 billion years ago. The Earth itself is only 4.5 billion years old, and for the first few 100 million years, the Hadean Eon, the surface was too hot and too chaotic to support life as we know it. This means that life appeared almost as soon as conditions permitted. It didn't wait billions of years. On Earth, microbial life persisted for about 3 billion years before complex multicellular organisms appeared. Intelligence, in the sense of technology producing civilization, emerged only in the last few 100,000 years, and technological civilization has existed for only about 10,000 years. If the jump from simple life to complex life is difficult, or if the jump from complex life to intelligence is rare, then most living worlds might be home to nothing more than microbes, a galaxy teeming with life, but not with minds. And if intelligent civilizations do arise, they might not last long. The Great Filter Hypothesis, one proposed solution to the Fermi paradox, suggests that somewhere in the chain from dead matter to spacefaring civilization, there is a step that is extraordinarily difficult, filtering out nearly all lineages before they can become visible on cosmic scales. That filter might be behind us, perhaps the origin of life, or the evolution of eukaryotic cells, or the development of multicellularity was the hard step, and we've already passed it. Or the filter might be ahead of us. Perhaps technological civilizations tend to destroy themselves through nuclear war, environmental collapse, or some risk we haven't yet imagined before they can spread beyond their home world. If the filter is behind us, the galaxy might be full of life, but few civilizations. If the filter is ahead of us, civilizations might arise frequently but burn out quickly, leaving the galaxy quiet. Either way, Andromeda's trillion stars would harbor life, but perhaps not the kind of life that builds radio telescopes and wonders about the universe. There is a deep loneliness in this picture, a universe filled with microbes but empty of minds, trillions of living worlds, each one blind and deaf and unaware of the other's existence, life everywhere, consciousness nowhere or almost nowhere. Just a few fragile candle flames of awareness flickering briefly in the dark, separated by gulfs of space and time, that ensure they can never know of each other. And yet there might be minds on some of those trillions of worlds. Intelligence might have emerged, beings might be looking up at their sky, seeing the Milky Way as a faint smudge, wondering as we wonder whether they are alone. The wondering itself is a kind of connection. Not a physical connection, light takes 2.5 million years to cross the gap, but a conceptual one, two civilizations separated by a void that neither can cross, asking the same question, feeling the same awe, experiencing the same loneliness. We will probably never know. The distance is too great, the photons are too few, the information is too sparse. Andromeda's potential inhabitants, if they exist, are as inaccessible to us as we are to them. We can speculate, we can calculate probabilities, we can dream, but we cannot know, and perhaps that's all right. Perhaps the not knowing is part of the experience. Perhaps the universe is constructed precisely so that minds can wonder without certainty, can ask without answering, can reach without grasping. The gap between question and answer, between yearning and fulfillment, this might be the permanent human condition, not a temporary limitation to be overcome by better technology, but a fundamental feature of existence in a cosmos of this scale. Let me talk about how we actually study Andromeda, because the methods are as remarkable as the results, and they illustrate something deep about the nature of science itself. Everything we know about Andromeda comes from light. Photons that left the galaxy 2.5 million years ago and traveled through the void to our instruments. We have never touched Andromeda, we have never sent a probe. We have only caught photons and read what they carried, but light carries an enormous amount of information if you know how to read it. The intensity of the light tells you how bright the source is. The wavelength tells you the temperature of the source. Hot objects emit shorter wavelength, bluer light. Cool objects emit longer wavelength, redder light. The spectrum, the distribution of light across wavelengths, is the richest source of information of all. Every chemical element, when heated, emits light at specific characteristic wavelengths, a fingerprint of spectral lines that uniquely identifies the element. By analyzing the spectrum of a star, you can determine its chemical composition, its temperature, its surface gravity, and its radial velocity, how fast it's moving toward or away from you. The radial velocity measurement is particularly important because it gives you the Doppler shift. When a light source moves toward you, the wavelengths of its light are compressed, shifted toward the blue. When it moves away, the wavelengths are stretched, shifted toward the red. By measuring the precise wavelengths of spectral lines and comparing them to laboratory measurements, you can determine the source's velocity along your line of sight to a precision of a few kilometers per second. This is how we know that Andromeda is approaching us at 110 kilometers per second. Its spectral lines are blue shifted by a specific measurable amount. Modern astronomy observes across the entire electromagnetic spectrum. Each wavelength range reveals different physical processes, probes different temperatures and densities, and tells a different part of the story. Radio observations at wavelengths from millimeters to meters reveal the cold gas and the magnetic fields. The 21 centimeter line of neutral hydrogen emitted when the spin of a hydrogen atom's electron flips relative to the spin of its proton maps the distribution of atomic hydrogen throughout the galaxy and far into the halo. This is the gas that hasn't yet condensed into molecular form, the reservoir from which molecular clouds and eventually stars will form. Radio maps of Andromeda show that the HI disk is warped, lopsided, and extends well beyond the visible stellar disk, evidence of past interactions with satellite galaxies. Carbon monoxide emission at millimeter wavelengths traces the molecular gas, the coldest, densest component of the interstellar medium, the stuff from which stars are actively forming. CO is used as a proxy for molecular hydrogen because H2, being a symmetric molecule, doesn't emit efficiently at the low temperatures of molecular clouds. CO is the next most abundant molecule and is easily detected, so astronomers use it as a tracer. Radio continuum emission, broadband radio radiation, not associated with any specific spectral line, comes from synchrotron radiation, relativistic electrons spiraling through the galaxy's magnetic fields, emitting radiation as they're accelerated. This emission traces both the magnetic field structure and the distribution of cosmic rays, high-energy particles produced primarily by supernova remnants. The radio brightness of a galaxy correlates with its star formation rate. Because more supernovae means more cosmic ray production and more synchrotron emission. Infrared observations at wavelengths from about 1 micrometer to a few hundred micrometers reveal warm dust and cool stars, dust grains heated by nearby stars to temperatures of a few tens to a few hundred Kelvin emit primarily in the infrared. These warm dust regions mark sites of star formation, places where young stars are still embedded in the clouds from which they formed, invisible at optical wavelengths because the dust absorbs their visible light. The Spitzer Space Telescope and the Herschel Space Observatory mapped Andromeda's dust distribution in exquisite detail, revealing the spiral arms and the star-forming ring with a clarity that optical observations cannot match. Near-infrared observations at wavelengths of 1 to 5 micrometers are dominated by the light of cool evolved stars, red giants and asymptotic giant branch stars, that emit most of their radiation at these wavelengths. By observing in the near-infrared, astronomers can map the distribution of old stellar populations, which trace the underlying mass distribution of the galaxy more accurately than the young, bright stars that dominate optical images. Visible light, the narrow band of wavelengths that our eyes can detect, shows the stars. Blue light comes from hot, young O and B stars, yellow and orange from medium-temperature stars like the Sun, red from cool red dwarfs and red giants. Color information, the ratio of blue to red light, distinguishes young stellar populations from old ones. The spiral arms are blue, the bulge is yellow-red. The color map of a galaxy is, in essence, a map of its star formation history. Ultraviolet observations at wavelengths shorter than about 400 nanometers reveal the very hottest stars, those with surface temperatures above about 10,000 Kelvin. These are the massive O and B stars whose ultraviolet radiation ionizes the surrounding gas and creates HII regions. UV observations are the most direct probe of recent star formation. The Galaxy Evolution Explorer GALEX mapped Andromeda in ultraviolet, revealing the star-forming ring and the spiral arms in stunning detail. X-ray observations from instruments like the Chandra X-ray Observatory and XMM Newton reveal the most violent environments. Gas heated to millions of degrees in supernova remnants, in the accretion flows around compact objects, in the hot halo of the galaxy emits X-rays. Chandra has catalogued hundreds of X-ray sources in Andromeda, X-ray binaries, where matter from a normal star falls onto a neutron star or black hole and heats to extreme temperatures, supernova remnants, where the expanding shock wave from a stellar explosion slams into the surrounding medium, and the central supermassive black hole itself, which occasionally flares in X-rays when it consumes a small amount of material. Gamma-ray observations from space-based instruments like the Fermi Gamma-ray Space Telescope probe the highest energy processes, cosmic rays, protons and heavier nuclei accelerated to relativistic speeds by supernova shocks, collide with interstellar gas and produce gamma rays through particle interactions. Gamma-ray observations map the distribution of cosmic rays and, indirectly, the sites of recent supernova activity. By combining observations across all these wavelengths, radio, infrared, optical, ultraviolet, X-ray, gamma-ray, astronomers construct a comprehensive, multi-dimensional portrait of the galaxy. Each wavelength adds a layer of information. Each layer reveals something that the others miss. The combined picture is far richer than any single wavelength's observation could provide. One of the most ambitious observational campaigns ever conducted on Andromeda was the panchromatic Hubble Andromeda Treasury, PHAT. This Hubble Space Telescope survey imaged a large section of Andromeda's disk in 6 filters, spanning the ultraviolet to the near-infrared, resolving individual stars with extraordinary precision. The resulting dataset contains measurements of over 117 million individual stars, their brightnesses in multiple colors from which their temperatures, luminosities, ages, and chemical compositions can be inferred. This is worth pausing to appreciate. 117 million stars, each one measured, characterized, placed on a color magnitude diagram, the astronomer's equivalent of a population census. By analyzing the distribution of stars on this diagram, how many hot blue stars, how many cool red stars, how many giant stars, how many main sequence stars, the PHAT team could reconstruct the star formation history of each region of the galaxy. The result was a detailed map showing when and where stars formed across Andromeda over the past several billion years. The picture that emerged was one of a galaxy that has been active throughout its history, but with significant variations in both space and time. Some regions experience bursts of intense star formation, possibly triggered by the major merger event, while others have been relatively quiescent. The star-forming ring at 32,000 light-years shows up clearly as a region of enhanced recent activity. The outer disk shows signatures of disturbance consistent with interaction with satellite galaxies. 117 million data points from a galaxy 2.5 million light-years away, extracted entirely from light. This is what modern observational astronomy can do. Let me talk now about the magnetic fields and cosmic rays that permeate Andromeda, because these invisible components play important roles in the galaxy's dynamics and are often overlooked in popular discussions. Galaxies are magnetized. Not strongly. The typical magnetic field strength in a spiral galaxy's disk is about 5 to 10 microgauss, roughly 100,000 times weaker than the Earth's magnetic field at its surface. But across galactic scales, even these weak fields have significant effects. They provide pressure support. A magnetic field exerts a pressure that can be comparable to the thermal and turbulent pressures in the interstellar medium. They influence the motion of charged particles. They affect the dynamics of gas in the disk and halo. The magnetic field in a spiral galaxy like Andromeda has a complex structure. On large scales, it follows the spiral arms. The field lines are stretched and amplified by the galaxy's differential rotation, wrapped into a spiral pattern by the same shear that creates the density waves. On smaller scales, the field is tangled and turbulent, reflecting the chaotic motions of the interstellar gas. The galactic magnetic field is generated and maintained by a dynamo process, the same basic mechanism that generates the Earth's magnetic field and the Sun's magnetic field, but operating on a vastly larger scale. Electrically conducting gas, ionized hydrogen and other elements moving through an existing magnetic field generates electrical currents that in turn amplify the field. The galaxy's differential rotation provides the energy input, stretching and twisting the field lines. Turbulence, driven by supernova explosions, stellar winds and gravitational instabilities, provides the mixing that prevents the field from simply winding up and decaying. Cosmic rays, high-energy particles, mostly protons and heavier atomic nuclei, traveling at nearly the speed of light, spiral along the magnetic field lines, confined to the galaxy by the field structure. Without the magnetic field, cosmic rays would escape into intergalactic space almost immediately. With it, they're trapped, bouncing back and forth along field lines for millions of years before eventually diffusing out of the galaxy. The primary source of cosmic rays is supernova remnants. When a massive star explodes, the expanding shock wave accelerates charged particles to tremendous energies through a process called diffusive shock acceleration. Particles bounce back and forth across the shock front, gaining energy with each crossing. The most energetic cosmic rays reach energies millions of times higher than anything achievable in terrestrial particle accelerators. They are the highest energy particles known to exist. As cosmic rays spiral through the magnetic field, they emit synchrotron radiation, electromagnetic radiation produced by charged particles accelerating in a magnetic field. This radiation is detected at radio wavelengths and is the primary tracer of both cosmic rays and magnetic fields in galaxies. The radio brightness of a galaxy's disk and halo maps the distribution of cosmic rays and the strength of the confining field. Cosmic rays also affect the chemistry of the interstellar medium. When a cosmic ray particle passes through a molecular cloud, it can ionize molecules, stripping electrons and creating reactive ions that drive chemical reactions impossible at the cloud's low temperature. Cosmic ray ionization is the primary source of ionization deep inside molecular clouds, where ultraviolet radiation from stars cannot penetrate. This ionization has consequences for the cloud's dynamics. It determines the coupling between the gas and the magnetic field, which in turn affects how quickly the cloud can collapse and form stars. Magnetic fields also affect star formation directly. A collapsing cloud of gas threads magnetic field lines through its volume. As the cloud contracts, the field lines are compressed and amplified. The magnetic pressure resists further contraction. The field pushes back against gravity. For star formation to proceed, the magnetic flux must somehow be removed from the collapsing core. The primary mechanism is ambipolar diffusion. Neutral gas particles, which are not coupled to the magnetic field, slowly drift inward through the ionized gas, which is coupled to the field. This gradual seepage of neutral gas past the magnetic field allows the core to contract and eventually collapse. The time scale for ambipolar diffusion determines, in part, the rate at which stars form. If diffusion is fast, magnetic support is quickly removed and star formation proceeds rapidly. If diffusion is slow, the field persists and star formation is delayed. Understanding this process is essential for understanding why galaxies form stars at the rates they do, why only about 1 to 10% of a molecular cloud's mass is converted to stars rather than all of it. Let me step back and think about what Andromeda tells us about the universe, not just about itself, but about the process of galaxy formation and evolution that has shaped the entire cosmos. Andromeda formed roughly 12 billion years ago, about 2 billion years after the Big Bang. At that time, the universe was a very different place. The cosmic microwave background, the afterglow of the Big Bang, was still relatively warm, and the first structures were just beginning to form from the tiny density fluctuations imprinted by quantum mechanics during inflation. Dark matter clumped first. Small dark matter halos formed, merged, and grew into larger halos, a hierarchical process, building big structures from small ones. That is the fundamental mode of structure formation in our universe. Within these dark matter halos, gas cooled and collected, forming the first stars and the first small galaxies. These proto-galaxies then merged with each other, building up larger galaxies over billions of years. Andromeda assembled through this process. It was not born as a single, fully formed galaxy. It grew over time through the accretion of gas from the cosmic web, the filamentary network of dark matter and gas that connects galaxies across the universe, and through the merger and absorption of smaller galaxies. The evidence for this assembly history is written in its structure: the stellar streams in the halo, the warped gas disk, the asymmetric spiral arms, the mix of stellar populations with different ages and chemical compositions. This hierarchical assembly is not unique to Andromeda. It is the standard mode of galaxy formation in the lambda CDM cosmological model, the current standard model of cosmology, which posits a universe dominated by dark energy, lambda, and cold dark matter, CDM, every large galaxy formed through a similar process of merging and accretion. The Milky Way, the galaxies in the Virgo cluster, the giant ellipticals in the centers of galaxy clusters, all assembled from smaller building blocks over cosmic time. Andromeda is special to us not because it's unique. There are billions of similar galaxies in the observable universe, but because it's nearby, close enough to study in detail. Close enough to resolve individual stars, map stellar streams, measure rotation curves, and reconstruct a formation history with a precision impossible for more distant galaxies. Andromeda is a laboratory, a place where we can test our theories of galaxy formation against detailed observations, checking whether the predictions of hierarchical assembly match the actual structure of a real galaxy, and largely they do. The simulations and the observations agree remarkably well. The dark matter halo, the disk, the bulge, the spiral arms, the satellite system, the stellar streams, all are reproduced, at least qualitatively, by state-of-the-art cosmological simulations. The agreement is not perfect. There are discrepancies at the margins, particularly in the number and distribution of satellite galaxies, but the broad picture is consistent. We understand in general terms how Andromeda formed. The details continue to be refined. Andromeda also occupies a crucial position in the cosmic distance ladder, the sequence of methods that astronomers use to measure distances across the universe. At the base of the ladder are direct geometric methods, radar ranging within the solar system, parallax measurements to nearby stars. These methods are precise but limited in range. Parallax works out to a few thousand light-years, useful within the Milky Way, but useless for measuring distances to other galaxies. Cepheid variables extend the ladder to nearby galaxies. Andromeda is close enough that individual Cepheids can be resolved and measured with the Hubble Space Telescope. The Cepheid distance to Andromeda, 2.54 million light-years, is one of the most precisely measured extragalactic distances in astronomy, with an uncertainty of only a few %. For galaxies too distant to resolve individual Cepheids, astronomers use even brighter standard candles, particularly type Ia supernovae, the thermonuclear explosions of white dwarf stars in binary systems. These explosions have remarkably consistent peak luminosities, making them visible across billions of light-years and useful as distance indicators. But type Ia supernovae must be calibrated. Their intrinsic luminosity must be established by measuring them in galaxies whose distances are already known through other methods, Andromeda. And galaxies at similar distances serve as calibration anchors for the type Ia supernova scale. Getting Andromeda's distance right is therefore essential for getting the entire cosmic distance scale right. An error in the Andromeda distance would propagate upward through the ladder, distorting every subsequent measurement, including the measurement of the Hubble constant, the rate at which the universe is expanding. The Hubble constant is currently one of the most contentious numbers in cosmology. with different measurement methods yielding slightly different values that are difficult to reconcile. The tension, called the Hubble tension, might indicate new physics beyond the standard cosmological model, or it might indicate a systematic error somewhere in the distance ladder. Either way, the accuracy of the foundation, including the Cepheid distance to Andromeda, is critical. I want to close with something that is less about physics and more about meaning, because Andromeda is not just an object of study, it is an experience. When you look at the Andromeda Galaxy, when you go outside on a clear, dark night and find that faint, fuzzy patch and let your eyes rest on it, you are doing something that humans have done for at least 1,000 years, since Al-Sufi's time and probably far longer. You are looking at the same object that every civilization in the Northern Hemisphere has had the opportunity to see, the same photons, or rather the same kind of photons from the same source, that entered the eyes of Persian astronomers, Chinese stargazers, Greek philosophers, medieval monks, Renaissance scholars, Enlightenment scientists, and now you. Each generation saw the same smudge. Each generation understood it differently. Al-Sufi saw a small cloud. Herschel suspected an island universe. Hubble proved it. Rubin revealed its dark matter. The Hubble Space Telescope counted 100 million of its stars. Each generation added a layer of understanding, building on the work of predecessors who often lacked the tools to test their own ideas. The knowledge accumulated slowly, painfully over centuries through the painstaking work of observers, theorists, instrument builders, and analysts, most of whom never received adequate recognition, and many of whom, like Henrietta Leavitt, were actively prevented from pursuing the full scope of their abilities. The understanding we have today, the detailed, quantitative, multi-wavelength portrait of a galaxy of 1 trillion stars, is the culmination of this 1,000-year effort. It is built on the shoulders of people whose names we know and people whose names are lost, on instruments that range from Al-Sufi's naked eye to the Hubble Space Telescope's 2.4-meter mirror, on insights that range from Leavitt's period luminosity relationship to the lambda CDM cosmological model, and it is still incomplete. We don't know what dark matter is. We don't know whether Andromeda contains life. We don't know the precise history of its assembly or the exact outcome of its future collision with our galaxy. The questions that remain are in some ways more profound than the questions that have been answered. This is the nature of science. Every answer reveals new questions. Every solved mystery uncovers deeper mysteries. The universe does not become simpler as we study it. It becomes more complex, more nuanced, more surprising. The more we learn, the more we realize how much we don't know. Andromeda embodies this. It is simultaneously one of the most thoroughly studied objects in the sky and one of the most mysterious. We can count its stars but not its planets. We can measure its mass but not identify its dominant component. We can predict its collision with us but not the fate of our descendants. The galaxy is a mirror. It reflects both our knowledge and our ignorance, both our capacity for understanding and our limits. When you look at Andromeda tonight, you are participating in a tradition that began before you were born and will continue long after you're gone. You are adding your observation to a chain that stretches back to Al-Sufi and forward to astronomers who will use instruments we can't imagine to answer questions we haven't thought to ask. You're also doing something that Al-Sufi could not do, understanding what you're looking at. When he saw a small cloud, he saw a mystery. When you see a faint smudge, you see a galaxy, 1 trillion stars, a supermassive black hole, spiral arms of gas and dust, and young blue giants, a halo of dark matter, extending 500,000 light-years into space, satellite galaxies being torn apart, stellar streams marking the graves of consumed neighbors, and the whole enormous structure falling toward you at 110 kilometers per second, headed for a rendezvous that was determined by gravity before either galaxy was fully formed. You see all of this in a smudge because someone 1,000 years ago noticed it and wrote it down, because someone a century ago pointed a telescope at it and resolved its stars, because someone decades ago measured its rotation and discovered its dark matter. Because thousands of scientists across dozens of countries, speaking dozens of languages, using instruments that span the electromagnetic spectrum, have spent their careers extracting knowledge from photons that left a distant galaxy before our species existed. The smudge is a galaxy. The galaxy is universe in miniature, a trillion stories unfolding over billions of years, most of which we will never know. And the fact that we know as much as we do, that we can look at a faint patch of light and reconstruct its structure, its history, its future, is one of the most remarkable achievements of the human mind. The light is still arriving. 2.5 million photons for every year of travel time landing on your retina, one at a time in the dark. Each photon carries a tiny fragment of the story. We've been reading that story for 1,000 years. We'll be reading it for 1,000 more. The galaxy doesn't know we're watching. It doesn't know we exist. It is vast and old and indifferent, a structure of 1 trillion suns orbiting in the dark, obeying laws of physics that were determined in the first fraction of a second after the Big Bang. And yet we watch, we measure, we wonder. We argue about dark matter and debate star formation rates and build telescopes and train students and write papers and give talks and record videos and try against all odds to understand something that is 2.5 million light years away and contains more stars than we can count in a human lifetime. This is what we are, dust that looks at distant dust and wonders what it's made of. Stardust, studying starlight, building a picture of the cosmos from photons and mathematics and an insatiable, irrational, magnificent curiosity. Andromeda is out there tonight. Go see it. It's been waiting for you since before you were born, since before your species existed, since before the photons that carry its image began their journey across the void. It's not going anywhere. Well, it is actually. It's coming toward you at 400,000 kilometers per hour. But you have about 4 billion years before that becomes a problem. Good night.